Morning, everyone. How are we doing? Questions while we wait for everybody to come in? How do we find? Let me answer Effie's question first. Why do we multiply a limit by its conjugate? This is a nice trick that is available to us that may be useful in the case that you have a 0 over 0 or infinity over infinity. You multiply by 1, so you're not changing anything, you're not affecting the term. This allows us to rewrite the argument, if you will, in another form, which may be easier for us to deal with. Somebody's asking about the derivative of this, and this is a good place to start. Let's work out the derivative of this function. For the web work, how many decimal points are required exactly, right? Who knows? Who knows? Which is why you should never enter decimals. You never know. One question, 2 decimals is sufficient. Another question, 8 is not enough. So who knows? Stop using a calculator and start using web work as its own calculator. Amy, send me an email. Is infinity plus infinity an indeterminate form? The answer is no. You can think of infinity as a very large number. So very large number plus another very large number, you're going to get a very large number. If you can do the web work easily, I think you're in a good place. That's where you need to be. And when I say easily, just by looking at the question, doing a few things on paper, without other resources, then you're good to go. Absolutely. I don't know what equation 2 is. If there's a number and it's divided by negative infinity, what happens? Exactly. Max, that's my question to you. Party time indeed. It is the weekend, right? We're looking for the derivative. And as you know, the derivative, by definition, as we saw it last time, is this. And let's plug everything in. Everywhere you see an x in your original function, you replace with x plus h. And you get this. were you going to do? I mean, if you plug in h equal to 0, you, of course, get 0 over 0. So something's got to be done. I'm going to suggest, in this case, maybe a common denominator for the numerator. Common denominator, of course, being the product of the two. And we get over the product and now the whole thing is divided by h, right? So in the interests of time here, you know where the h is going, right? If this is divided by h goes on top or on the bottom, you know exactly where it goes. It goes on the bottom. And if you plug in h equal to 0, I mean, again, well, not again, but, well, yes, in fact, again, this goes to 0, so numerator goes to 0, denominator goes to 0, you still have a 0 over 0. What are we going to do now? Well, as was suggested before, now we'll multiply by the conjugate. Exactly, Matthew, thank you. Let's multiply by the conjugate, right? Again, just a nice trick that allows us to rewrite this expression in a different form. You multiply by 1, so you're not changing anything. How's the numerator going to 0? Well, this h goes to 0. So then you have square root of 1 plus x minus square root of 1 plus x. So just 0. Right? And you know what multiplying by the conjugate does. It essentially gets rid. How do you get from line 3 to 4? 1, 2. Wait, is this 3? 3 to 4 right here. Common denominator. Common denominator for the numerator. And then this h goes into the denominator. Right, so from here to there. Common denominator for the numerator. And then the h moves to the denominator. And then we FOIL, exactly. Do that, and you know what you get. You essentially get rid of the square roots. The 1 plus x minus 1 plus x, these are going to cancel, leaving you with a minus h on top. The h and that h is going to cancel, and then you no longer have a 0 over 0. The numerator is just negative 1. So this limit is going to be negative 1 over whatever the denominator is. X plus square root of x plus 1 times square root of x plus 1 is x plus 1. And here you have square root of x plus 1 plus square root of x plus 1. So two of these. Or if you prefer, negative 1 over 2, x plus 1 to the 3 over 2. There it is. Very nice. Exam type of question. All right. Let me take this time to introduce a definition. If the derivative exists, we say f of x, well, exists at some point A, we say f is differentiable at that point. We have other notation for the derivative. What did we introduce? We introduced f prime, really as the only notation for the derivative. Let me introduce the notation df dx, or dxf, or df. These are all notation for the derivative. Also, if y is equal to f of x, the derivative may be denoted dy dx as well. The x is just a subscript there, dx. Yeah. These are all notation for the same thing. Y primed as well, thank you. Y primed, yes. I was going to forget that. D as in derivative, absolutely. But, I mean, let's understand why this notation, where does it come from, right? This dy dx business. Remember that the derivative is really the rate of change, right? The change in y over the change in x, right? We introduce this delta y over delta x business, or f of x plus h minus f of x over h. If you think of the approximation to the tangent line, right? So the derivative is what is happening to this as delta x is getting smaller and smaller. So d instead of delta. That's the idea. How are we doing here? Questions? Let me, what do I want to do? Let me point out observe that if you have suppose you have two functions, f and g, which are differentiable, meaning that both of their derivatives exist. observe that the derivative of the sum which is the limit of f of x plus h plus g of x plus h minus f of x plus g of x all over h, you can split that up into two limits. Since both of these limits exist by the assumption that both f and g are differentiable. This is the derivative of f. This is the derivative of g by definition. So the derivative of a sum is the sum of the derivatives. Right? It comes as no surprise because you knew this to be true in the case of limits, right? The limit of a sum is the sum of the limits. And the derivative being really just a limit, this principle extends to derivatives. Similarly, if c is a real number, and f is differentiable, then the derivative of c times f, what is that? Let's work it out. This is c f of x plus h minus c f of x over h, and you can pull out the c. And this limit exists. And you know that you can pull out constants. So this is really c times the derivative. So the derivative of a sum is the sum of the derivatives. The derivative of c times a function is c times the derivative of that function. These two properties together are known as the linearity property of multiplication. And this goes back to the linear algebra thing, right? That linear portion. The derivative is linear. Have we already discussed what makes a function differentiable or not? Well, I mean, I gave a definition. A function f is differentiable if this limit exists, if the derivative exists. But let's observe now another thing, well, maybe two other things. Differentiability of a function, right? Whether a function is differentiable or not really depends on whether this limit exists. And this being a limit, you know that there's an epsilon delta definition for limits. Consequently, this translates to an epsilon delta definition for the derivative. I won't state it. We're not going to spend any time on that, but there is one. However, let's go back to if f of x is differentiable. And to answer Maxwell's question, what makes a function differentiable? A function is differentiable if its derivative exists. So if this limit exists. Exactly that. But now let's take a step back and just look at this limit for a moment. As h goes to 0, the denominator goes to 0. So Maxwell, of course, is asking the question, you know the limit of a product is the product of the limits. Is it also true for the derivative? The answer is no. The answer is no. We'll convince ourselves of that momentarily. But consider this. If this limit exists, since the denominator is going to 0, you know that in your work with limits, if the numerator doesn't go to 0, if the numerator approaches anything other than 0, you're going to have a number over 0, which is going to be some sort of infinity. So if this is to exist and be a finite value, we need the numerator to go to 0. But this limit does not depend on h. This limit is constant. Doesn't depend on h. So this is going to be f of x. So this is really limit as h goes to 0 of this part minus f of x equal to 0. Or if I bring this to the other side, we have this. The limit of f of x plus h as h goes to 0 has to be f of x. And if you think about this for a moment, this is really the condition that f is continuous. Still no answer to whether epsilon delta will be on the midterm. But I mean, the midterm is still 3 weeks away, so there's still time to make an announcement. Right, so what are we saying? If the function is differentiable, it had to be continuous to begin with. So this is a very nice observation. So immediately, if your function is not continuous, it cannot be differentiable. Questions here? Well, I mean, the question arises naturally. Are all continuous functions differentiable? An obvious question, right? Are all continuous functions differentiable? And the answer is no. Consider the absolute value of x. Consider the absolute value of x, which you know can be split up as a piecewise defined function, right? We've seen this before. Where Michael is suggesting that the derivative at 0 will not exist. We'll see that. We'll see exactly that. So consider this function at x equal to 0. First of all, you know the graph of this function, right? This is the function, and I can draw it without lifting the pencil from the paper. So this function is continuous everywhere. Michael is suggesting that the derivative does not exist at 0. And let's show that. What is the derivative at 0? Well, by definition, this is the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. Right? I mean, we're used to doing it for any value of x, but if you plug in certain values of x, you're going to get the slope of the tangent line at that point. So if you plug in now, right, what is f of h? Well, it's just absolute value of h. F of 0, you know the absolute value of 0. That's just 0 over h. So this is the limit we're looking at. Limit of absolute value of h over h. You know what to do. You know what to do. You're going to evaluate this limit by considering the limit from the left and the limit from the right. So consider the limit from the right for values bigger than 0. Absolute value of h is just h. And that limit is 1. How did you get absolute value of x? I'm suggesting, I mean, it's just an example. I'm giving you an example of a continuous function which is not differentiable. So limit from the right is 1, limit from the left. For values less than 0, absolute value of h is negative h. And in that case, we get a limit of negative 1. Conclusion. Conclusion, limit from the left and limit from the right are not equal. This limit does not exist. But that limit was the derivative at 0. The absolute value of x is a function, is a continuous function whose derivative at 0 does not exist. How we do? 。 People seem to wonder where this absolute value of h is coming from. We're using the function absolute value of x. That's what we're starting from. Where did I lose you? What does undefined or does not exist actually mean? Well, it means that the function does not have a derivative at 0. That's all it means, right? And you know, from the graph, what happened? You had this corner happening at 0. This idea can be generalized. When you have a corner, when you have a corner, the derivative does not exist. The derivative existing, right? I mean, we saw if the derivative exists, your function had to be continuous. The derivative is actually a bit stronger. It's a smoothness condition. It's a smoothness condition, and here your function is not smooth. There's a corner happening. So if you have a corner, the derivative is not going to exist. If you have something that is known as a cusp, the derivative is not going to exist either in a similar fashion, right? I mean, this is still continuous. I drew it without lifting the pencil from the paper, but the derivative will not exist here either. So the idea of differentiability is a condition of smoothness. Is your function smooth? Here it is not. How are we doing here? Questions? Anybody? How are we doing with the definition of the derivative? Are we moving on? Not all functions are differentiable. Well, I mean, that's exactly the point of this example. Not only are not all functions differentiable, because as soon as your function is not continuous, it's not going to be differentiable at points of discontinuity. But this function is continuous everywhere. And even that is not strong enough because it's not differentiable at 0. All right. Well, so somebody's asking, is x squared differentiable at 0? Why don't we check? Let's just quickly work out the derivative, see what happens. I won't do it for 0 specifically. Let's do it for all values of x. And let's see that this function is differentiable for all values of x. What is f of x plus h? Everywhere you see an x, you replace with x plus h. So we get x plus h all squared minus x squared over h. Expand that. This is x squared plus 2xh plus h squared minus x squared over h. The x squares cancel out. Now let's factor out an h from both numerator and denominator. I'm seeing a lot of talk about epsilon delta. Do you want to do an epsilon delta definition example with the derivative? We can always do that. factor out an h. The h's cancel out nicely. And as h goes to 0, we have a 2x. Notice that, so what are we saying? We are saying that the derivative of x squared is 2x. This is regardless of the point x. Right? The derivative of x squared is 2x. So if x is 0, the derivative is 0. The slope of the tangent line is 0 at 0. Right, this is the graph. Continuous, because I can draw it without lifting the pencil from the paper. The slope of the tangent line at the origin is going to be 0. Right, this is a rule which gives us the slope of the tangent line at every single point. This is yet another notation. Right? If x is 1, so at the point 1, when x is 1, at the point 1, the slope of the tangent line is 2, and so on and so on. So, we introduced the definition of the derivative as this limit. Again, being a lit, you can easily imagine that it has an epsilon delta counterpart that we did not write down and we're not going to discuss. But, if you're interested, it's there. And for those of you who know a little bit about calculus, you understand that we're not going to spend the whole course coming back to this definition. Instead, we're going to look at rules for differentiation. And let's start on that journey immediately. That being said, though, you can always come back to this definition that I'm erasing. This is first principles, and it always applies. We'll be coming back to it throughout the course, but it's always there in the back of our mind, and we can always use it. Claim. The derivative, if C is a real number, the derivative of C is 0. The derivative of a constant is 0. Let's prove it. And we're going to prove it using the limit definition. Let f of x be equal to c. The derivative is the limit of f of x plus h minus f of x over h. F of x plus h, everywhere you see an x in your function, you replace with x plus h, but there is no x. So f of x plus h is just c. F of x is c. And so this is 0 over h, which is just the function 0, whose limit is 0. The derivative is 0. There it is. The derivative of a constant is 0. We will now use this as a rule. But is an h 0? So don't you really have a 0 over 0, right? A good question. But the denominator is approaching 0. It's never actually 0, right? It never reaches 0. But the numerator is 0, and 0 over any non-zero number is 0. So this is the function 0, whose limit is, of course, 0. Let's look at the graph to really understand what is happening. You have the function c. So you have a straight horizontal line, y equals c. Right? F of x is c. F of x plus h, it's still c. So the slope is 0. The slope of the tangent line is 0. Well, I mean, if you were asking how we got f of x plus h to be c, you see it now from the graph. Right? So this, the line joining these 2 points, it has slope 0. So the limit of that is going to be 0. The derivative of a constant is 0. What did we see? We saw a few moments ago the derivative of x squared as 2x. We saw last time the derivative of square root of x was 1 over 2 root x. Did we do this last time, square root of x? I think we did. Let's look at the derivative. I think we had done the derivative of 1 over x as well. Am I? Yes or no? Wait, no, we did not see that? Some people are saying yes, some people are saying no. I don't know. We did last class. I'm probably pretty sure we did. What? Pretty sure we had done it. Square root of x we did see. We saw the x squared a moment ago. Not the 1 over x. Very well. So why don't we do the 1 over x? By definition, it's this. And this is 1 over x plus h. Minus 1 over x all over h. Let's put the numerator over a common denominator, which is going to be the product, x plus h times x. So we get an x minus x plus h on top. And this h goes back in the denominator right here. The usual, right? And what do we have? Open up the brackets. The x's cancel out nicely. And we get a minus h over x plus h times x times h. The h's will cancel. And now as h goes to 0, this goes to 0. So you're left with a minus 1 over x squared. where am I going with this? Where am I going? We're saying the derivative of x squared is 2x. The derivative of x to the 1/2, which is what that is 1/2 x to the minus 1/2. The derivative of the derivative of x to the minus 1 is minus 1x to the minus 2. I'm trying to see a pattern arising here, and I think we see it, right? If you have x to some power, you bring the power down and you subtract 1 from the power. Let's write that as a rule. The derivative of a power of x is nx to the n minus 1. You can prove that from the definition of the derivative. It's a bit difficult to work out, but it's doable. I won't prove it, but we'll take that as a rule. I too believe it's known as the power rule. I don't usually refer to it as a name, but there it is. Let's call it the power rule. So let's use that as a rule, coupled with the fact that the derivative of a constant is 0, and the fact that the derivative is linear, meaning that the derivative of a sum is the sum of the derivatives, and the derivative of c times a function is c times the derivative of that function. So let's now use these 4 rules of differentiation, which can all be proven. In fact, we proved most of these using the definition, right? So let's use these 4 rules now to do some exercises. Differentiate the following functions. All right. Differentiate the following function. First of all, you can treat it as the sum of 2 functions. So if you're looking for the derivative of a sum is the sum of the derivatives, right, by this property. And now you've got a constant times a function. So you can, by this property, pull out the constant. This is 5 times the derivative of x plus 4 times the derivative of x squared. But the derivative of x, by this property, you bring the 1 down. This is 5 times 1x to the 1 minus 1, which is 0. And here, sorry, I'm missing a prime here. The derivative of x squared, bring the 2 down and subtract 1 from the power. So in other words, this is 5 plus 8x. 5 plus 8x, exactly. Thank you, everyone. And there it is. You could, of course, prove this from the definition, right? Limit as h goes to 0 of g of x plus h minus g of x over h. Simplify, you will get exactly this. How are we doing here? Aiden, I'm justifying everything here as a first step for those of you who have never seen this before. But of course, we're going to, as with limits and everything else we've done, as soon as we've understood, we're going to stop justifying everything and just get through these quickly. In fact, I'm going to even do that now. Right? The derivative of a sum is the sum of the derivatives, so I can do each separately. I can take the derivative of this, plus the derivative of this, plus the derivative of that. And here, it says 7 over 4 is a constant. So I can take it out and just do the derivative of x squared. We just saw the derivative of x squared is 2x. Here, this minus 3 is a constant. I'll leave it and take the derivative of x. What is the derivative of x? Derivative of x is 1. Derivative of 12. What is the derivative of 12? 12 is a constant. The derivative of a constant is 0. There it is. This is 7 over 2x minus 3. Again, it's a nice exercise to do this derivative from the definition and make sure that you're able to get this as the answer. Seven over 4 is a constant. So you can take the constant out and just differentiate the function. How do we get 7 over 2? Well, 7 over 4 times 2. 4 is 2 times 2. So I can cancel one of the 2's. There it is. Right? The derivative. I mean, I've rubbed off the rule, but I'm sure you still have it. The derivative of x cubed, bring the 3 down and subtract 1 from the power. 3 minus 1 is 2. Derivative of e cubed is 0, thank you. E is 2.71 something, something, something. So e cubed is going to be, I don't know, around 18 or something. But the point is, it's a constant. The derivative of a constant is 0. So this is 3x squared, and there it is. Georgia is asking, why is 7 over 4, in this case, not equal to 0? We saw that the derivative of a constant times a function, in fact, we proved this using the limit definition, that you could take out the constant. Right? It's because c is multiplying some function of x. Here, this constant, or even here, this 12, we also proved that the derivative of a constant was 0. These are not contradictory terms here, right? Because here there is no x, right? This was a straight line, whereas this is like the function, but multiplied by some constant. How come you cannot use the power rule for e cubed, right? I mean, we're differentiating with respect to x here. This is df dx. How does your function change with respect to a change in x? This function does not change. This function does not change. This is a constant number. This is a constant function. Straight function, horizontal function. There is no change. The change is 0. Matt is asking the excellent question, what if it was x cubed plus e to the x? What if this 3 was an x? We'll discuss that in a moment. But before we do so, let's consider this function. Don't let the z fool you. Right here, z is the independent variable. So here we're going to treat z as we did x here. And we're going to ask the question, what is the derivative? And when we say derivative, we, of course, mean derivative with respect to z. So the z is taking the place of the x here. So whatever rule you had in terms of x, of course, you have the same rule in terms of z. So this power rule, you bring the power down, minus 5 z to the minus 6, right? You subtract 1 from the power. Let me write it as this, right? Because our rule, the derivative of x to the n, is n x to the n minus 1. And same thing here, bring the power down, 1/2 z to the 1/2 minus 1. So this is minus 5 z to the minus 6 minus 1/2 z to the minus 1/2. No point in rewriting anything here. Let's leave it as that. Consider this. No need to do anything here. This is an acceptable answer. In high school, it was just another way to give you an extra exercise to do. I'm happy with that for now. I mean, sometimes it does become important to do other things. And if this had been a regular class to sit in midterm or final, you know, again, you would have had multiple choice questions and anything could have been the answer. So you would have needed to be able to go from one to the other and so on. This is coming from page 181. So derivative here, root 2 is a constant, right? So we'll just take the derivative of x, and the derivative of x is 1. Derivative of this is 0, and we're done. Absolutely. Somebody was asking what the derivative of e to the x was, and I claim the derivative of e to the x is e to the x. We're not yet in a position to prove that, but let's give some sort of justification for this. So I won't call it a proof, but rather a justification. If I define f of x as e to the x, let's try to work out the derivative using the definition. So this is e to the x plus h minus e to the x over h. And notice you've got an e to the x in the numerator here, in both terms. So why don't I factor out an e to the x? This will leave me with e to the h minus 1 over h. And in fact, if you replace e with any base a, the same idea can be done here. Right? You'd have a to the x times this, a to the h minus 1 over h. So, conclusion, the derivative of e to the x is going to be e to the x times whatever this limit is. So e to the x times some number. And in fact, e is such that this limit is equal to 1. This can actually be used as the definition of e. E is this number such that e to the h minus 1 over h, the limit goes to 1 as h goes to 0. So let's use this as an added rule now, along with all the other rules that we have seen. Let's incorporate that into our rules, and that is exactly that, right? That's why we call ln the natural log. It comes up naturally, right? This is a very natural condition. We ask, what function is its own derivative? It's a natural question to ask, and e to the x is the answer. People are asking, how does this limit equal to 1? Like I said, we're not in a position to prove that. But if you look at this, right, like I said, I mean, this argument can be repeated for any value of a. Blah, blah, blah. A to the x plus h minus a to the x. Factor out an a. And you get this. The obvious question that arises, is there a value of a for which this is equal to 1? If so, then this limit will be a to the x for that value of a. And the answer is, there is. E is that value of a for which this limit is equal to 1. Like I said, you can use that as the definition. You can search for a value of a which makes the limit equal to 1. Consider this. Consider this, same question, right? What is the derivative? Well, I mean, I keep using the same two notations for derivative. Let me change it up a bit. What is the derivative? Derivative with respect to t, right? I mean, you understand again that t is the independent variable here. That's a t in the power, not a plus. The plus, of course, would not make any sense, right? What is the derivative? This is, of course, you know, if you want to take a moment to rewrite this, this is t to the 1/2. So the derivative, you bring the power down and you subtract 1 from the power. The -2 is just a constant, and you can take the derivative of e to the t, and we just saw that the derivative of e to the t is e to the t. So there it is, 1/2 t to the -1/2 minus 2e to the t. How are we doing here? Let's consider 24. Right, I mean, I was expecting some buffering moments ago. Who knows? We didn't. We did not. And that's the point. We're back. Thank you. Excellent. All right. So we're looking for the derivative. Now, it's very important in these types of questions that you don't start inventing your own rules. Here we have a quotient We don't know how to take the derivative of the quotient yet. But it doesn't matter. Well, I mean, that's the point. We haven't seen the quotient rule, and we don't need the quotient rule here. What you want to do is rewrite this in a fashion that you can treat. What do we have? We have the derivatives of powers of x. So let's rewrite this as powers of x by splitting it up into two fractions. And if you split it up into two fractions, this business here is really x to some power. What power? You know. -3/2. And this is x to the -1. Thank you, Guillaume and Michael. And rewriting it in this fashion, now you can use the power rule. Right? So here, there was nothing we could do. We didn't know how to treat that, but luckily for us, we can rewrite it in a way that's manageable with the knowledge we have right now. And that's what you're going to want to do for these exercises. If you are just differentiating powers of x, we're good to go. If you're differentiating something weird, you want to rewrite it in a way that you can deal with. What is the derivative here? We're going to treat this last term, which is equivalent to the original, right? But now at least we can deal with that. Bring the power down. -3/2. Subtract from the power to get x to the x to the what now? X to the, you know what it is. -5/2, thank you. And do the same for the other one. Bring the power down. -1, x to the -1 minus 1, which is -2. There it is. Why couldn't we apply just the original rules? Well, the original rules have to do, what do the original rules say? They tell you that the derivative of a power of x is nx to the n-1. They tell you that the derivative of a sum is the sum of the derivatives. They tell you that the derivative of a constant times a function is the derivative of the function times a constant. And we also saw that the derivative of e to the x is e to the x. These are the only rules we have so far. Well, actually, derivative of a constant is 0. So those are really the only rules we have so far. Here, viewed as a quotient, we don't have a rule which tells us what to do. But we can rewrite it in a way that it's a sum. So you could take the sum of each of these, and each of these follow the power rule. So we're good to go. Here, this square root of 5x is a bit problematic, right? But let's rewrite it as square root of 5 times square root of x. And now there's no more problem. Let's take it one step further and rewrite this as root 5 times x to the 1/2. And this root 7 x to the -1. We haven't done the derivative yet, right? We haven't differentiated anything. We have just rewritten the function in a more manageable way. So now we can differentiate. And the derivative, constant times the power of x. We're going to leave the constant aside. And differentiate x to the 1/2, which is 1/2 x to the -1/2. Leave the root 7 aside. And differentiate the x to the -1, which is -1 x to the -2. And if we clean that up, root 5 over 2, x to the -1/2, minus root 7, x to the -2. How are we doing here? Let's do a few more, and then we'll move on to what's the derivative? Derivative of e to the x is, you know what it is. It's e to the x. We have it right here. The derivative of e to the x is e to the x. The derivative of x to the e right? This is x to some number. The derivative of x to some number, you bring that number down. And you get x to that number -1. There it is. Consider this. How was the number e invented? Well, I mean, if you look back at the proof, we were looking for a value such that a to the h minus 1 over h is equal to 1. You could use that as as to how E was discovered. We were looking for a value of A for which this limit is 1. Consider this. It's the same question, right? We're looking for y prime. But now you have an e to the x plus 1 business. We know the derivative of e to the x is e to the x, but does this plus 1 change anything? And if so, how? And what's going on? We can't just pretend it's not there. We have to deal with it systematically. But you know that e to the x plus 1 is really e to the x times e to the 1. And this e to the 1 is just a constant. Very nice, Matthew. Right? This e to the 1 is just a constant. So the derivative of a constant times e to the x, we're going to leave the constant aside and just differentiate the e to the x, whose derivative is e to the x, and then differentiate the 1, whose derivative is 0. And so we see that the derivative of this is just e to the x plus 1. We can only use the rules that we have at our disposal. Don't be making up your own rules. That's always the danger here. Consider this. Find the tangent line to this function at the point 0, 2. Michael is asking about the derivative of e to the x squared. Let's not worry about that for now. We'll get to it, just not right away. We're looking for the tangent line, and you know the derivative gives you a rule for the slope of the tangent line. So let's find the derivative. What is the derivative? We'll forget this 2 and just differentiate e to the x. The derivative of e to the x is e to the x. Plus the derivative of x is 1. This is the rule which gives us the slope of the tangent line at every single point. So when x is 0, y prime of 0, when x is 0, this is 1. So we get 3. 3 is the slope of the tangent line. So your tangent line, which has the form y equals mx plus b, well, we now know that m is 3. Your tangent line has to go through the point 0, 2. So when x is 0, y is 2. So it's easily seen that b is 2. And if we put everything together, y equals 3x plus 2. 3x plus 2, y equals 3x plus 2 is the equation of the tangent line. Look, I'm seeing a lot of questions about the derivative of e to the x squared, the derivative of e to the 2x. Let's not worry about those quite yet. Those are coming up. These are excellent questions. But we don't have the tools yet to find their derivative. Possibly next week. We'll probably get there by next week. Let's not worry about it exactly as Victoria is suggesting. It's known as the chain rule. Let's not worry about it for now. Let's make sure we understand what's happening here, and then we'll let's do one more example. Find the tangent and normal lines. I haven't defined what a normal line is yet, but as Nandini suggests, the normal line is the line that is perpendicular to the tangent. So if this is the tangent line, so this is the tan line, the normal line is going to be perpendicular to the tangent. And as you know, perpendicular lines, you know how these are related. Their slopes are negative reciprocals of each other. They multiply to give you -1. Let's start with the tangent line. And you know how to find the tangent line. The derivative gives you the slope. The derivative, dy dx. And this is the power of x. We'll bring the power down. 3 over 2, x to the what now? X to the 3 over 2 minus 1. X to the 1/2, thank you. Why don't I introduce a bit of notation here while we're here. dy dx evaluated at the point 1, 1. Right, this straight vertical line means evaluated. So when x is 1, we get the slope 3 over 2. 3 over 2 is the slope of the tangent line. So your tan line, y equals mx plus b. M is actually 3 over 2. And it has to go through the point 1, 1, right? So when x is 1, y is 1. So b is easily seen to be -1/2. And consequently, your tangent line has the form 3 over 2x minus 1/2. No, this is our last example. We're already way past. our time. There it is. Normal line has slope negative reciprocal of this. So if you flip it and throw in a negative, what is the slope of the normal line? You tell me. Negative 2/3. Right? Flip the fraction and throw in a negative. Normal line has this slope, and consequently, let me not call it B, let me call it C here. Negative reciprocal. The two lines are orthogonal to each other. Negative reciprocal, flip that, and throw in a negative. When x is 1, y is 1. So C is easily seen to be 5/3, and the normal line has equation negative 2/3 x plus 5/3. There's no 3/3 here. It's 3/2. It's the derivative. The derivative when x is equal to 1. The derivative gives you the slope of the tangent line. Derivative is this in general. It's a rule that gives us the slope of the tangent line. When x is 1, you get 3/2. How are we doing here? This is a good place to end. I much prefer this slope-intercept form. Please try to write your answer in this form. All right, you guys have a good weekend. Email me if you have any issues, and go ahead and practice these rules for differentiation. I will see you guys on Monday. You guys have a good weekend. See you then.